Okay. Gonna need a hot one for this. Hot cup of tea, that is. We're starting string theory. Decided to do this because I've wanted to do it for a while. Gonna have it be a regular thing, probably maybe twice a week or so. And string theory. Before we start, what I want to say about string theory is that there's a lot of people, a lot of famous people out there who talk about string theory. They talk about the intricacies behind it. They talk about, they don't really talk about the intricacies behind it. They talk about it sort of in a general fashion. People like Brian Greene, people like Leonard Susskind, people like Brian Keating, people like Neil deGrasse Tyson, all these people, they talk about string theory as if it's like this end-all theory or a theory that just doesn't work. One of the people that I've sort of been following for a while is Eric Weinstein, and Eric Weinstein is one of the people who's sort of championing this idea of string theory is dead. We have to move on. However, I feel over the years, as I've studied string theory, that I sort of have a love-hate relationship with it, and that the mathematics is certainly quite interesting. However, it does seem like a dead-end theory. I'm not really a string theorist, but I can do the best I can to understand the complex math behind it. And with that being said, we can go ahead and get started on this. It's probably going to be a long journey to understand this theory. However, I don't have limited time to do this. I have unlimited time to do this. In fact, this might be a long playlist because there's so many rabbit holes we can go down. But we're going to do that. We're going to do exactly that. We're going to go, we're going to see how far deep into each rabbit hole we can get without really calling ourselves actual string theorists. My view on this whole thing is I feel like string theory should be more of a hobby, because if you're trying to make your job out of it, I don't know, to me it seems like it would be an unfulfilling job. String theory seems something like something that I would do while I'm on the beach. Maybe I'd be doing some derivations or something like that on the beach. I don't think I'd get satisfaction out of studying this for a living. But anyways, let's have some tea and get into this. Why talk about string theory? After all, it seems like a dying theory. However, it is my belief that in order to progress into the future, we need to understand what didn't work in the past, so that we don't repeat it. As the old cliche goes, those who don't study history are doomed to repeat it. We need to know the theories that didn't work in order to avoid them in the future. However, string theory offers some mathematical insights that we need not dispense of. If it is for these main reasons, again, I have a few typos in this, but that's fine. It is for these main reasons that I think that it is necessary to keep string theory at the top of our minds. So let's go ahead and dive in. My main sources are going to be these PDFs and books that I have showing on the screen right now. I particularly like Barton Zweibach's book. That's just a personal opinion of mine. But then there's some other, let's point out some other stuff here. This unreasonably quick introduction to string theory, conformal field theory, and geometry is quite good as well. It's fairly short. It's 2024 also. It's 1994 paper. What is string theory? This is another pretty good one. This guy here is a little bit complex, but we'll take stuff out of this as well. And string this David Tong, obviously this is probably the go-to for most people when it comes to studying this theory. But we're gonna dive straight into this. In this first video, we're gonna cover just the special relativity. We're gonna go over special relativity in this video. We're going to go over light cone coordinates in the next video, and then we're going to tie light cone coordinates in with energy and momentum in the next video. We're going to, and we'll keep on going from there. So let's go ahead and get started on the special relativity. This is really just a review. So in this video and in some of the following videos, where again this is just going to be a review on special relativity. So let's go ahead and get started. In special relativity, we're dealing with four-dimensional space called space-time. This was the big thing that Einstein proposed back when he was doing his stuff back in the 1915 and 1920s and so forth. There's a Lorentz invariant object in special relativity called the space-time interval. Let's unpack this statement. So we want to know what a Lorentz invariant object is, and we want to know what a space-time interval is. Here's our space-time interval. I have necessary equations numbered as well. Our space-time interval is really just the difference between our temporal component. Our space-time interval is going to be an interval between two vectors, two objects, if you will. Both objects have a temporal component and three spatial components, and the sign on the temporal and spatial components are opposite one another. And we're going to see why this is the case in a bit, but we're starting sort of at. I'm presuming you kind of know what this is already. If not, we'll establish this, because I'm trying to start from first principles ish, but I don't want to start from bare bones first principles, because then we'd be here all day going over special relativity, quantum mechanics, and so forth. So I'm supposing that you know a little bit of special relativity right now, and we'll build on this later. So this can also be rewritten in this way. Notice I don't have this written here, but this here, dx mu dx nu, let's unpack this, and we'll see how this statement is related to this statement right here. So dx mu dx nu is the same thing as writing dx mu dx nu with this Minkowski metric. This Minkowski metric is going to raise the mu, right? Just because here, whenever I type these variables, this guy here, let's do a different thickness in my pen color. So this guy here and this guy here should be the same, and this is what this Minkowski metric effectively raises our index, and we'll see how this works in a matrix way, because really what this should come down to is matrices, because I think it's relatively easy to understand matrices, or not. Yeah. So we have our dx mu, okay, is going to be a row vector with this uppercase, and then we'll say this is going to be a column vector. Right? Maybe I said that opposite. This is right, so this is a column, this is a row, and here's our Minkowski metric. Right, so our Minkowski metric is going to be this minus sign, and these guys here are going to be positive signs. When we do this multiplication, this guy here times this guy here, well, this negative sign is going to turn this into a positive sign, and all these are going to become positive as well. Then we multiply this by this guy here, this, which is right here, this times this. We take, right, this guy, multiply it by this guy multiply it by this guy multiply it by this guy, and this guy multiplied by this guy. That's just basic multiplication of a row vector and a column vector. And when we do that, we get the next line, all right, which is this. And we've seen that this is this up here. All right, so dx mu lower dx nu, or dx subscript mu, is this guy right here. Let's continue. So let's put a pin in this, and we'll come back to it. But let's review the concept of time dilation, because this is important, especially when it comes to understanding light cone coordinates, which is what we'll talk about in the next video. In special relativity, because we need to understand, so we need to understand this because in order to understand special relativity. So we start with comparing two situations involving a light beam. So here's our light, our little star of light. It's traveling this way and it's going to travel this way again. So it travels a distance of 2L, okay? at a rate of c. So distance divided by rate is going to give us the time it takes for the light to get from here to here and then back to here. All right. And along this axis, we have the spatial coordinates along the horizontal axis, and along the vertical, we have our temporal components. All right. So now let's suppose our light is traveling like this, where it moves in time, it moves in space. Okay. Here, our light was not moving in space. Here, our light is moving in space, but it also moves in time because it's moving up as well. So we can calculate the L squared to be, just by Pythagorean theorem, this squared, which is right here, plus L squared, which is right here. So little l is the actual distance the light travels. Big L is just the vertical distance between the two mirrors, if you will. Pretend these are mirrors. And so by Pythagorean, so this is our Pythagorean theorem. We then take the square root of both sides. We get this. Since our light beam is moving two of these arrows, right? 1, 2. We need to multiply this by 2 to get the total distance traveled. So the total distance traveled is also equal to the rate of the light times the amount of time it takes to get from here to here. And we're going to call that t moving, or t subscript m. Okay, so this is t moving. All right. Okay, so then we take this, so that's all equal to this here, and then we square both sides. So the square of this side, we get this, square of this side, we get this, because 2 squared is 4, and then everything within the square root goes away. And then what we do is we can divide this by 4 to get rid of this 4, and so we get this. Then we want to bring Tm to one side, so we have this and this, because we subtract this from both sides of the equation, and so we get just L, big L on the side of the equation. Then we can then take out dt m squared, right, and we get c squared over 4, u squared over 4, and again u is that's the rate that the particle of light travels in the x direction. Okay. So we have this, and now we get to here. We just divide both sides, multiply the top and the bottom by 4 over c squared. 4 over c squared. This is effectively multiplying by 1. Right, so we could say we multiply the top and bottom by 1. And then when we do that, we get this, right? So because 2 squared is 4, that's going to give us this 4 right here. We have our L squared, which is L squared here, and then C squared, which is going to give us this. And then here, down here, we get our 4s are going to cancel, C squares are going to cancel, so we have this 1. And then we have our U and our C. Okay, and this could hold for any particle, which is why we have a U here. So for a U, if U was the rate, it was C. If this was C, then this is going to be 1, and then so we're going to get the square root of 0. Okay, so that's in the case for light. In the case for a particle that's not light, then U is going to be different. It's going to be much. If U is like the rate of U walking, it's going to be much lower than that of C. All right. And so so this is our time dilation formula. Right? This is our famous time dilation formula. It tells us that the sense of time that a particle is moving in space experiences is different than that if it was standing still and just traveling in time. Right, so I like to think of this as a particle. Its internal clock is going tick, 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 tick. But if it's moving, it's going tick, tick, tick. It's different. Okay, the degree by which it's different depends on how fast it's moving. Okay. So with this, we can begin to understand Lorentz transformations. In special relativity, we also want to know the velocity of things relative to a moving frame of reference. And so our frame of reference is just moving in x. And so if our frame of reference is just moving in our x direction, we could say that dt is equal to gamma times the dt prime, right? So this thing down here is gamma, right? So this thing is going to be related to gamma. Specifically, gamma is 1 over 1 minus u squared over c squared. All right? And I'm drinking some tea as I'm doing this because I like tea. And so we have, so this is gamma, right? So this whole bit is gamma times our still frame. The velocity of the frame itself, because you can imagine you have a particle traveling, but also the frame is also traveling. Okay, so we need the velocity, we need to subtract the velocity of the frame and the position of the object in that moving frame as well. Right, so because the object has a position in the moving frame, but also a position in the still frame. Right, so, and then we divide it by the rate, because if you look at this, if you just do some dimensional analysis, this has a unit of time. Okay. Another way we can write this is this way, where beta is going to carry. Beta is really just the carrier for for all the information we know about the moving frame, right? What I'm saying there is that beta is Vx over c. Okay, so that's beta. We do the same thing then for dx. If our frame is just moving in x, then we do the same thing, right? So we have our Lorentz, or no, okay, we haven't really talked about Lorentz Lorentz transformations yet, but we have this is really just, we have time dilation again, right? So, but we also need, so this is dx, so we need to multiply this by dx, right? So, let me explain this a little bit better. This is the, this is the position of our particle in the still frame, and then the position of our particle in the moving frame, and then this is the velocity of the moving frame and the time it takes in the still frame. So this should actually be a prime, I think. Yes, that should be a prime. Everything with a prime is going to be with respect to the moving frame, okay? And so, yeah, that's right, because then we get this, okay? These two guys are going to stay the same because our frame is only moving in x, not in y or z, okay? All right, so if we want to find the velocity of the object in the frame that is not moving, we just need to calculate this object then. And so this object is no prime on this guy, no prime on this guy. All right, so we divide this thing by this thing, and that's what we got for these two guys. And then we divide everything. To get from here to here, we're multiplying actually by dividing, right? We're dividing everything by this, essentially, right? It shows up in the denominator on both. Okay. And then, so here then, we can see that here is our velocity in our prime frame, or our moving frame. And this is just 1, right? So it's 1 times Vx. So this is the velocity of our frame in x, right? Velocity of our frame in x. Okay. And then everything else, right? So all this is just this right here, right? Because we have 1, and then this is Vx, and then Ux over c. This is going to carry over since these are all going to be Ux, right? All the denominators here. But then we have this, we add these two guys for dy and dz. And you can do this, right? You just need to know these two guys, and so you can do a similar calculation like this, and what you get is these guys, right? Because you won't have two gammas. You'll have one gamma, right? You'll have this gamma, which is where this guy mass comes from, right? So these are the velocities of our particle in our still frame. Okay, all of this can be codified into a matrix. That matrix looks like this, and we can see this, right? Because when we do the multiplication of this matrix on our prime frame, we get this, and this matches this. These two guys match along with these two guys match, right? Okay, so again, we said this is our moving frame, and this was our still frame. All right. Okay, this is where things get interesting, right? We want to call this a Lorentz system. So this obeys the invariant line element, and we can see this. We can see this with equation 1 here. So equation 1 again is this guy. All right. So let's focus on these two guys right now, because these two guys really are the ones that are, there's some crazy stuff going on here, right? We have gammas, we have betas, and we can see. So let's do this. So let's take these two guys, flesh them out. We get these two, right? Because x naught is this, x1 is this guy, okay? So we multiply, we square them, right? We're squaring this, and we get this. We're squaring this, and we get this, okay? Then we can subtract the two, right? This subtraction element is right here, okay? And then when we subtract these guys, we get gamma times this minus this. That's these two guys, right? So this minus this, that's that minus that, right? These two guys are going to cancel, right? Because this minus sign makes that a positive, and then this minus this is this minus this. Okay. All right, and then we can see that so we have the gamma, our x naught. So we have x naught here, and we have an x naught here. So we could take x naught out, and we could say that x naught times 1 minus beta. Same thing for x1, 1 minus beta squared. And then we get this guy here, right? Because we can take out the 1 minus beta squared, and we get this right here. But gamma squared times 1 minus beta squared. Well, gamma squared we said was up here, but this thing we said was beta, right? So u over c was beta. That's the same thing as vx over c. That's the velocity of our particle with respect to, or not with respect to, but the velocity of our particle over the rate of the light. All right. So this thing here multiplied by this, well, this was what was in the denominator, and now we're multiplying it by that. So this actually just goes to 1, and so we can see that this actually works, right? Because we've recovered these two guys. So we've essentially said that when we subtract this and this, we get this and this, okay? And then the rest, those are going to be the same, right? This, because they don't change, okay? The dx and dy, or dy and dz coordinates, again, they don't change, and so when we look at equations 4, and therefore, when we look at equation 4, right, so equation 4 is, again, right here. The the space-time line element remains unchanged upon the change of a moving reference frame traveling at a constant velocity, which is described by our matrix, which we'll call the Lorentz transformation. So an object, again, nothing's really being transformed about the object. We're just moving a reference. We're moving a frame of reference, and that movement of the frame of reference is going to help us define what a Lorentz transformation is. It's the transformation of the positions and velocity and sense of time that a particle understands or feels with respect to that moving frame. By measuring in that moving frame, that's what we're calling a Lorentz invariant or a Lorentz transformation, right? So the Lorentz transformation is just a transformation from a still frame of reference to a moving frame of reference going at a constant velocity. All right. In general, a Lorentz transformation must obey the following property. It has to preserve the Minkowski metric. Okay, so the Minkowski metric multiplied by whatever Lorentz transformation matrix we have times the transpose must equal the Minkowski metric. So this is the most general condition that we're going to stipulate to be a defining feature of our Lorentz transformation. We can take the determinant of both sides then. When we do that, the determinant of the transpose of any matrix is going to be just going to be the determinant of the matrix itself, because you just transpose. Whenever you take the determinant, it's going to be the same thing. And so we get 1, right? So because this is the same thing. These two L and L transpose are the same thing. So it's just going to be determinant squared equals 1. So take the square root of both sides. You can have plus or minus 1 being the determinant of L. This means that the determinant of a Lorentz transformation must have a determinant equal to plus or minus 1. We can note, therefore, that the rotation matrices have a determinant of 1 and therefore qualify as Lorentz transformations as well. So our Lorentz transformations can move along X, they can move along Y, they can move along Z, but they can also rotate, okay? And those rotations also constitute a valid Lorentz transformation to describe our particle. Okay, so the rotation matrices, just in summary, because we're not going to go through all of these. This is like special relativity 101. We're doing string theory here, so I'm just going to give these matrices to you up front here. Rotation matrices: rotation around X, rotation around Z, rotation around Y, boost over in X, boost in Y, boost in Z. These, I'd have to double check. These are all relative. All these transformations are relative anyways, but these are what the forms of these are going to look like, and you can double check these as well. This is our gamma matrix. This is our beta, okay? And at every point in space-time, we can construct vector spaces. And in the case of special relativity, we'll also have our Minkowski metric ready to construct an invariant object out of any one of these 4 vectors. So we have our Lorentz transformations; those are our boosts and our rotations. We also have our these guys right here. This is all conducive to special relativity. It's all conducive to preserving the Minkowski metric and making the line invariant object. That's what this whole video is really about. And then we also have these vector spaces that we can put every point in space and time, which is these vector spaces are, we have a 4 vector. Each one is a 4 vector, so all these vectors live in 4 dimensions. And some of the most common examples we'll come across are position, energy, momentum, electromagnetism, and current density, 4 vectors. And each one of these is going to have a Minkowski metric at some point x mu, okay? So all of these are fields, right? All of these are fields, or vector fields. Okay, we have x mu as a function of some point in space, which is described by x mu. J described at some point x mu. A at some point x mu, and p also. This is a little bit abstract, but this is just, I kind of wanted to just put this in here just to give you a sense of what is a good visual summary to get a feel of what special relativity is like. Okay, because we're not going to really dwell on special relativity for too long here. Anyways, let's go ahead and stop here. These first few videos are going to be free. You can go onto my YouTube channel. You can go onto, or you're on my YouTube channel, right? You can, I'm having a little space brain right now, but you can become a member. You can also become a member on Patreon and contribute there as well. Just the first few videos here are going to be free. Then we'll start charging. So with that being said, let's go ahead and stop here. I'll see you guys in the next video. Bye.